Welcome and good morning. Can you hear me? Can you hear me? Welcome. Dinesh, please sit down. Everyone sit down. We're all set. We've got on wheels on Skype. And let's hope that technology is going to work. If it doesn't, we'll just have to invent something. But I'm sure it will work. We've tested it. And we're very pleased to be able to have Ron Wills, who I think is to some extent like the father figure for Bioconservacion. He was due, I heard him speak here 2 years ago. He was due to speak at my conference, Logistics Hub, Fruit Logistica last week, and he couldn't make it. And so we are just looking forward to the experience that, the results that Ron has collected for pineapples, leading on from your presentation, Gonzalo, yesterday, to fill in some details and research data.
Yeah. Okay. Ron, whenever you want.
Okay, thank you. You can hear me okay now? Can you hear me okay? Gonzalo, can you hear me?
Yes. Yes, we hear
Hello?
you perfectly. I'm going to mute our mic. Okay, so we hear you perfectly. Go ahead, please.
Okay. Right, first of all, I'm very sorry that I wasn't able to be there with you in person, but life has many unpredictable twists and we cope the best we can. This is the first time I've done a presentation like this on Skype. It seems a bit strange talking into a computer screen, but I hope it goes well enough that I can get across a message that I want to convey. Well, I want to start by putting my work into some historical context. 1958 was the year that I started being involved in post-harvest horticulture research. So 2018 is actually 60 years since I started on post-harvest horticulture. And in the 60 years since, I've seen some amazing advances. When I started work, most produce was sold fairly close to where it was produced. It was sold fairly soon after it was produced, and quality was quite variable from good to just edible. We're now in a situation where we've got an expanded trade reach where you can really get any produce anywhere in the world. The season is much longer, and for many produce, even though they're highly seasonable, you can get them for 12 months of the year. Top quality is now the expected norm. There's no room in the marketplace for sub-quality produce. In the 1940s, when my mother used to send me up to the fruit shop, I was supposed to ask for the third grade produce because we were not very well off. You just don't get that in the stores anymore. Now, much of this development has been attributed to the development of the cool management chain, where from operations on the farm right through to the home, produce is managed at the appropriate temperature. However, there's a limit to what temperature management can achieve. And there's also a new paradigm, environmental sustainability. And under this environmental sustainability, industry is under pressure to reduce energy usage, firstly to reduce costs, but also to be seen as socially responsible. But both these factors provide an opportunity for alternative low-cost technologies. And from our perspective, we're particularly interested in ethylene. Ethylene is one of the simplest organic compounds, but it's quite remarkable. It's actually one of the defining differences between plants and animals. Ethylene has no function in animals, but it's active at all stages of plant development and has a controlling role in seed germination right through to cell death. I want to start with the action of ethylene on climacteric fruit, even though this talk is about non-climacteric produce, because the effect of ethylene on climacteric fruit is well accepted by industry. You're all aware of climacteric fruit, found to go marked changes in colour, texture and taste during ripening. The ripening process itself is initiated by the natural synthesis of ethylene. Now, the ethylene level that initiates ripening in fruits is very well documented, and industry is reasonably well organised so that many fruit are harvested and stored unripe. They're inhibited from ripening during storage or marketing by either maintaining a low ethylene concentration or holding in an environment where the produce are less sensitive to ethylene, and they're ripened just before marketing often by adding exogenous ethylene. When we come to the effect of ethylene on non-climacteric produce, and non-climacteric produce can include a number of non-climacteric fruit, and I've just listed a few of those. All the vegetables are non-climacteric, but what we're calling vegetables here are non-seeded plant parts. The things that are marketed as vegetables that have seeds, such as tomatoes and cucumbers, are actually classed as fruits, and they can either be climacteric or non-climacteric. Most flowers are non-climacteric, although there's a few, such as carnations, which are climacteric. Now, the feature of non-climacteric produce is that they are all harvested at edible maturity, so you don't want any change after harvest. They have a very low natural synthesis of ethylene, and because of the fact of low synthesis of ethylene and you don't want any change, industry tends to discount the importance of ethylene. But we ought to look at where are the sources of ethylene that affect produce. Of course, it can be produced by the produce itself. It can be synthesised by other produce in proximity, like in the marketplace or in storage chambers. It can come from exhaust gases from motor vehicles, particularly forklift trucks, or it can come from leakage of natural gas pipes or gas cylinders, or just as general industrial pollution of ambient air. Now, produce react to ethylene concentration. It's irrelevant the source of the ethylene. It's the concentration in the atmosphere which causes changes in all produce, climacteric and non-climacteric. So what is the effect of ethylene concentration? As the concentration rises, the rate of deterioration increases, whether we're talking about colour change, loss of texture, rotting or development of off flavours. It raises the question, is there a low concentration where ethylene has no effect? For many years, the threshold level used to be considered 0.1 microlitres per litre or 0.1 parts per million. And we've worked over many years to try and convince, firstly, researchers and also industry that ethylene is active at much lower concentrations. We had an experimental model where we held ethylene in an airstream at a certain rate. We often used 20 litres an hour. We used a logarithmic range of ethylene concentrations of 1, 0.1, 0.01 and 0.001. Now, the lower level is there based on our ability to detect ethylene. Our limit of detection is about 0.005 parts per million. So when we talk about 0.001 parts per million, we're really saying it's less than 0.005. Now, this limit of detection is very important. I'll come back to it later in the talk. We then monitor the quality of produce over time and determine the time to become acceptable, which we call the storage life. Now, we examined quite a lot of different non-climacteric produce, and I've just presented the data for the yellowing of lettuce at 20 degrees, the rotting of strawberries at 0 degrees, and the development of chilling injury in oranges at 2.5 degrees. And you can see in all cases, when you reduce the ethylene concentration, the storage life increases in a linear fashion. Now, this is a logarithmic scale, so it's exaggerated so that small differences at this end are equivalent to large differences at the top end. So that you get the same benefit in increasing storage life as you go from 1 part per million to 0.1 parts per million. It's the same as when you go from 0.01 to 0.001. Now, the graph is still increasing. We can't measure any lower, but I wonder how much further benefits you can get if you can actually control the level of ethylene at lower levels. Now, I said previously that people thought 0.1 part per million was the threshold level. What I've done on this table is taken the data we obtained for a range of non-climacteric produce, what the storage life was at 0.1 parts per million, and what it was at 0.001 parts per million. And at ambient temperature and low temperature, I've plotted the days increase we get as you reduce from 0.1 to 0.001 parts per million, and I've also converted it to percentage gain in storage life. Now, it's quite variable, but I've taken an average at the bottom, and you can see the overall benefit is quite substantial, where we're getting 80% increase in storage life at ambient temperature and 60% at low temperature. Now, you don't want to take these figures as being literal, but you could say there's about a 2/3 increase in shelf life in non-climacteric produce as you go from 0.1 part per million to 0.001 parts per million. Now, the benefit of reducing ethylene in storage, of course, depends on the concentration of ethylene around the produce during storage and marketing. So what we did was we measured ethylene at 700 sites in the Sydney wholesale markets, in distribution centres, storage rooms, retail outlets, and even in domestic refrigerators. And we found every site we measured, all 700, at greater than 0.005 parts per million. In other words, we could measure ethylene in every storage or marketing situation. 0.1 parts per million we found to be a common level, and we even found 1 part per million in some fruit-related areas. So putting these two facts together, what does it mean? It means that any ethylene greater than 0.001 parts per million enhances senescence and ripening. In all market situations, ethylene is greater than 0.001 parts per million, and it's often present at 0.1 part per million. So we can say that storage life is suboptimal in all post-harvest situations. Therefore, any reduction in ethylene in the current marketing and storage situation will be beneficial. The question we can then raise was, how do you sell this to industry? And what we've tried to do is to try and create some standards for ethylene. In the earlier slide, I showed you the graphs of increasing storage life for different produce as you decreased ethylene concentration. Now, we collapsed all these lines into one equation. We said, let's say that 100% of potential market life occurs when the ethylene concentration is 0.005. So that becomes 100. We adjusted the equation for all the values further down, and we produced this equation, which I've given in the top right-hand corner. We then said, well, it's not achievable to expect to always get 100% of potential market life. Well, we could say it would be acceptable if you got 90%. of potential marketable life. And if you come along here, the ethylene concentration at which you achieve this is 0.015 parts per million. At the bottom end, we could say, well, you'd say the storage situation would be unacceptable if you've lost 1/3 of the potential storage life. So we've taken this point here, we've come along and it comes down to 0.1 part per million. So we've used these as our proposed standards for ethylene for non-climacteric produce. So that if you want the greatest retention of top quality produce, you need to store produce at less than 0.015 parts per million, and under these conditions you'll have less than 10% of the potential post-harvest shelf life lost during storage or transport. However, for an unacceptable rate of quality loss occurs if you store above 0.1 parts per million, because there you get 30% loss of potential post-harvest life. So to me, you could go and put these as these are what you should be aiming for in a storage situation. Right, so that's sort of the background theory which then stimulated our work to go and look at particular commodities and how this might be applied. And the first group I want to look at is some of the opportunities to extend the market life of non-climacteric produce by reducing the ethylene in current marketing system. In other words, the industry can do what it's doing now, you just introduce a step which reduces the ethylene concentration. And the first example I want to use is with mandarin. This is internationally increasingly popular citrus fruit, and if not now, I think it'll soon will be the most popular citrus fruit for fresh fruit eating as distinct from processing. We did a large study on the Moroccan cultivar R4O, which I've shown in the top right hand corner. It also so happens I put a copy of the latest edition of the post-harvest book which John Golding and I wrote, and you can see this was published in 2016, and we've actually used the R4O mandarin on the cover photograph. Now the R4O in Australia is exposed to long-term and short-term storage for the local market and also long-term storage for export. Now the recommended storage temperature is 5 degrees, but because of the range of marketing situations that the fruit undergoes, it's exposed to a range of temperatures in various post-harvest operations. So what we did, we stored the mandarin at the same 4 ethylene concentrations which we use in all our studies, and all the ones from here on in will use it as well. And we stored the fruit at 20, 10, 5 and 0 degrees C, and we examined external, internal quality over 10 weeks of storage. Now, summarising the findings, we found that at all storage temperature, when you reduce the ethylene, you decrease respiration, you decrease visible deterioration of the calyx region, which is the button area, you decrease the ethanol accumulation in the juice, you decrease the rate of loss of eating quality, and you decrease rind pitting, which is, to us, is chilling injury. But the quality attribute that limits the storage life differs between different temperatures. For the mandarin stored at 20 degrees, the rate limiting step was the development of calyx mould. At 10 degrees it was taste acceptability, and at 5 and 0 it was chilling injury or rind pitting. The quality retention was always optimised at the lowest concentration. So our message was you want to ensure that ethylene is maintained equal to or less than 0.01 parts per million at all stages of the handling system, regardless of whatever the temperature is. Now, it's very hard to show all the results because you'd be looking at sort of a series of 3-dimensional graphs. So I've just put up the data we got for 7 weeks. And I've shown in the top left-hand corner the data for respiration. Respiration really reflects general metabolism in the tissue. And you can see that as the ethylene concentration goes down, the respiration goes down. Of course, it's much higher at 20 and you get much stronger effects. So the higher the temperature you're storing it, the greater benefit from a reduction in respiration by reducing ethylene. In the bottom left-hand corner, I've got the data for calyx mould. Now, it's only for 20 degrees because the mould only occurs when you hold mandarins at 20 degrees. And so it's really relevant for mandarins that are marketed directly from farm to market without any storage, or there's some hold up in the marketing chain. At 7 weeks, you can see the mould is almost 100% when you've got 1 part per million ethylene, and it goes down to about 40% at the very low ethylene. Of course, fruit stored at 20 degrees we said was unsaleable after 4 weeks, so obviously this is beyond sort of use by date. With the sensory score, this is essentially unacceptable taste or taste quality. You can see at 10 degrees at 1 part per million ethylene, it's really unacceptable. The sensory score ranges from 1 to 5, so it can't get any worse. Whereas at the low ethylene at 7 weeks, it's quite good, and it's almost as good as if you hold it at 0 or 5. Now, if I'd have showed you the data for 10 degrees, 10 weeks of storage, you would have seen that the sensory score at 0.1 parts per million would be up here somewhere. Now, with Ryan pitting, it's chilling injury, so it only occurs at 0 and 5, doesn't occur at 10, but you can see at 5 degrees, which is the recommended storage temperature, if you reduce the ethylene, you greatly reduce the amount of chilling injury. Well, the next example I want to talk about is strawberries at consumer level. Supermarkets in Australia say that the most complaints by consumers about fresh fruits and vegetables is with strawberries. They complain that the eating life is too short after they take it home. Now, it's well established that reducing ethylene at the packing house extends the market life of strawberries, and buy-on sachets have been utilised by a number of your colleagues in various markets. But we wanted to look at, is there a benefit if consumers add the sachet after they purchase it? And I put this note in red that this is preliminary data because the research is still in progress. So what we did was we went to the retail store, we bought a bundle of strawberry punnets, we added a buy-on sachet, a 5 gram sachet, into half of them when we purchased them, and we stored them at 5 degrees, which is the temperature of the domestic refrigerator. And at various times we counted the number of berries that we considered were acceptable for consumption. You can see the buy-on sachet works quite well. This is the decrease in acceptable berries with the control punnets, and when you add the buy-on sachet, the rate of decrease is much slower. Now, to get a quantifiable effect, I've said, well, let's say the consumer says they don't like it when there's 60% acceptable berries. So we can come along here, and this time we can say is the shelf life of the control berries, whereas here is the storage life of the berries with the buy-on sachets. And what we've done is the buy-on has more than double the consumer life. At 60% acceptable berries, we've increased the shelf life for the consumer from 2 days to 5 days. The consumer will consider the 2 days unacceptable, but I think would find 5 days quite acceptable. The graph at the bottom shows that we measured the ethylene concentration in the punnet. And you can see we've reduced the ethylene but we've only reduced it from 0.07 parts per million to 0.05 parts per million. So it's quite a small reduction, but it emphasises what I was saying earlier, the value of reducing ethylene at very low levels. Most people in their measurements would say wouldn't be able to pick up this difference, but that small difference has more than double the shelf life of the berries as far as the consumers are concerned. Now since then we've done another 3 batches of berries, and we're going to do another 2, which is why we've got the gap at the end. And this was dated, we finished last, or a week before last, just before I was due to leave Sydney. That's the trial I talked about before. Then I talked about 60% acceptable berries. We've upped the standard now and saying we want to know the time for 75% acceptable berries. And you can see in each of the 4 trials, adding the Bion sachet markedly increases the time for 25% berries to degrade. Now the last graph, I've taken the mean value of those 4, and you can see that the Bion sachet has increased the shelf life for consumers from 5 days to 8 days. In other words, we've got a 60% increase in life for the consumers. The question we then asked ourselves, well, are the 5 gram Bion sachets cost competitive for a retail market? Now, I don't know what the cost would be to retail it, but one of the options were, well, can the cost be reduced by having less absorbent? But here we were quite interested that we call them, or you call them, 5 gram Bion sachets. They're actually 6 gram Bion sachets. All the sachets we had all had 6 grams in them. So what we did was we made our own sachets with less Bion, and we used Tyvek that Steve Brabs from DuPont had sent us. And we put our own sachets into punnets of 200 gram strawberries, but we stored them at 20 degrees because we wanted an answer quickly. The graph shows the ethylene that accumulates inside the punnets at day 1 and day 2 when there's no Bion, and the sachet contains 1, 2 or 3 grams of absorbent. And you can see that adding in the Bion reduces the ethylene concentration, but there's no further decrease from 2 to 3. So to us, you only need 2 grams of Bion absorbent in the sachet for the length of time the strawberries are being stored. Right, the other example in this category of introducing ethylene reduction without changing the normal marketing systems, pineapple. It's not my work. The organisers of the meeting asked me to review this paper, which was put out by Costa Rica University, and I'm going to do this at the end of this current presentation, but this is where it fits. Right, so the next area we wanted to look at was, okay, is the cool chain technology always required? Now what we need cool chain technology to do is to meet market need. But we need to only meet market need. It doesn't really need to exceed market need. The cool chain stores produce at what are considered recommended storage temperatures. But these temperatures are developed by researchers to indicate the maximum market life that you can achieve. But most produce are marketed well before the end of the possible shelf life. So since you don't want the maximum market life, why don't you use less extreme temperatures? Now reducing the ethylene level gives a similar effect to reducing the temperature. You get an inhibition of ripening, senescence and rotting. So our next research question was, what is the interaction between temperature and ethylene with storage time? Now, while this presentation is about non-climacteric produce, the first commodity we looked at was banana, and I want to quickly just go through what we found with bananas. We examined the time to ripen of bananas at the 4 ethylene concentrations and at 3 temperatures, 15 degrees, which is close to the normal refrigerated transport temperature, and 20 and 25, which is sort of ambient type temperatures in temperate and warmer climates. And from the graph you can see that as you decrease the temperature and you decrease the ethylene concentration, the time to ripen increases, but it's not a linear function. We've generated the equation from this data, and you can see it's related to the log of the green life and the log of the ethylene concentration. Now, I won't go through how we apply it to various situations, but with Australian bananas, which are currently all transported in these refrigerated containers with 2 containers pulled by a prime mover, which we call B doubles, they move the fruit to 3,000 kilometres from the producing areas into the major markets in Sydney and Melbourne. But we showed it was quite easy to move them to market without refrigeration. Now the advantage, I guess, to the grower, a non-refrigerated truck costs 25% less to hire than a refrigerated. So they made a saving of 25% just by changing the vehicle they use. We then modelled it on international shipping, and we took the going from Latin America to Europe taking 21 days. We modelled the temperature you might encounter en route, and we asked the questions, can you transport bananas in containers without refrigeration? Our response was it's possible, but it's demanding. And we felt you needed some backup system to ensure that the ethylene remains low during the voyage. When we were concluding this study, we were told that many of the transporters or traders are now starting to put bananas into sealed plastic bags, where you generate a modified atmosphere of increased carbon dioxide and reduced oxygen. If you have a sealed bag, now studies were done in the lab that I was working, it wasn't my work, but it was other people's work in the 1970s, which showed that if you used a sealed plastic bag, it would keep the bananas green for 20 to 22 days at the temperatures we're likely to encounter, so you could just get there. But if you added some ethylene control into the bag, you definitely didn't need refrigeration. Now, this is a message, I guess, which is still need to percolate out and be tested by industry. All right, so we then went and looked, well, what was possible with non-climacteric fruit and vegetables? The first example I want to use is with green beans. Green beans, the deterioration is due to yellowing or rotting. The recommended storage is 5 degrees C because any lower and you get chilling injury. We stored them in our 4 ethylene concentrations and at 5, 10 and 20 degrees, and we got this pattern where again we get a marked increase in storage life as you decrease the ethylene concentration, as you decrease the temperature. The green beans are very sensitive to ethylene. Now the way this data is useful is we can generate the regression equation like we did for bananas. Now any trader knows that to send produce from here to there, you need so many days here, so many en route and so many at the marketplace. So the storage life is fixed for any particular situation. What we can do from the equation is calculate the combinations of temperature and ethylene concentration that you will achieve this storage life. And in this slide, the table below, I've shown this for a storage life of 14 days and 21 days. You can see that if you want a storage life of 14 days, you can't tolerate 1 part per million even if you store it at 5 degrees. Now, as the ethylene reduces, you can increasingly tolerate a higher temperature. Now, if you could store the beans at 0.001 parts per million, you could get a storage life of 14 days if you stored it at 18 degrees C. Now, in Northern Europe, and parts of the States, this is ambient temperature. So there's no need or a low need for refrigeration in these circumstances. Now, going to the more demanding storage life of 21 days, and from what Anoop tells me, this is what you need to ship beans from Kenya to the UK. You can see you can't tolerate 1 part per million or 0.1 parts per million, but if you could maintain the beans at 0.1 part per million ethylene, you could store them at 8 degrees C. And if you could keep them at 0.001 part per million, you could store them at 13 degrees C. Now, allowing yourself some extra storage life for unexpected delays, you could say if you could hold the beans at 0.01 part per million ethylene, you could transport them at 5 degrees and get them to the UK in good condition. If you could hold them at 0.01 parts per million, you could ship them at 10 degrees C. Right, looking at broccoli, and here the deterioration is yellowing and rotting, and the recommended storage temperature is 0 degrees C. This is the data we got from our 4 ethylene concentrations and 4 storage temperatures of 10, 20, 10, 5 and 0. And you can see at 0 degrees and 0.001 parts per million, you can get a storage life of 64 days. But who wants to store broccoli for 60 days? Now the recommendation is 0 degrees, and even if you had 1 part per million, you can still get 40 days storage life. And I again ask the question, who wants to store broccoli for 40 days? Now from this data we generated the equation, regression equation, and we translated it into storage life of 7, 14 and 21 days. And these are the temperatures you get at the particular ethylene concentrations. And you can see at any market life, whether it's 7, 14 or 21, as you move from 1 part per million ethylene down to 0.001 parts per million ethylene, you can increase the storage temperature by 4 degrees. So whatever market life a trader wants, if you can control the ethylene, you know you can come down 4 degrees from 1 part per million down to 0.001. Now, if you were to maintain broccoli at the lowest concentration of 0.001, you can see if you wanted a 14-day market life, you could store the broccoli at 9 degrees. Even if you wanted 21 days, you only need to store it at 6 degrees. Now, there's got to be a cost saving over storage at 6 degrees versus 0 degrees. And while we haven't done this sort of work, I found this paper by Kitterman and colleagues from Germany who went through this exercise with the storage of apples. What they did was they stored apples for 7 months in low oxygen, and their 2 treatments are storage at 1 degree C, which is the standard, and they stored them 5 degrees after fumigation with 1 MCP. Now, most of you will be aware that 1 MCP or 1-methylcyclopropane inhibits the action of ethylene, and I guess it's a competitor product to Bioconservacion products. But by inhibiting the action of ethylene, it's equivalent to removing ethylene. So we could say their treatment is equivalent to storing the apples in 0.001 parts per million. So they measure the energy consumption over 7 months, and they measured it at each stage of the refrigeration cycle. And you can see the green bars, which are the energy consumption at 1 degree, are higher than the energy consumption of the MCP treated apples that were stored at 5 degrees. They then totaled the energy consumption, and they found that the energy consumption at 5 degrees after treatment with 1 MCP was 20% that at 1 degree C. Now, when you talk to industry about storing high temperatures, they say, oh yeah, but you won't get the same quality of fruit. Now, Kitterman and his colleagues actually measured fruit quality after the 7 months. And I put some of the data here. And I put it for the two varieties, John Gold and Panova. And you can see, say, a firmness with John Gold. The fruit stored at the higher temperature was much firmer. There was no difference in rots. But the taste panel preferred to buy the fruit stored at the high temperature. The purchase preference was rated from 0 to 1. 0 was, oh, I'd never buy this, and 1 is sort of brilliant, I'd always buy this. So you can see 0.82 was quite a good score. Now with the Panova apple, there was there's only a small difference in firmness, but there was a big decrease in the amount of rots, and there was still an increase in purchase preference. So their findings were not only was there an 80% reduction in energy usage, but the fruit quality was actually superior or not inferior in any aspect to storage at 1 degree. So it's a double-edged benefit to industry. You can save most of your energy and your fruit quality will actually be better. Well, the next aspect we moved on to was, is it possible to have unrefrigerated marketing in tropical regions? Refrigeration is often either not accessible or not affordable in rural areas of many developing countries. So the produce is exposed to temperatures of 30 degrees plus and you get rapid deterioration. We want to look at, can ethylene control provide a sufficient extension in market life? This would allow the growers or traders to market their produce to more distant markets, or even to provide more flexibility in when to sell on local wet markets, so they could remove it for a day or 2 or 3 when it's in glut supply. Well, the first commodity we looked at was cucumber. And the recommended storage temperature for cucumber is 10 degrees C. It develops chilling injury at lower temperatures, and at higher temperatures, yellowing terminates the storage life. Now this is the data we got for the 4 concentration of ethylene when we stored them at 30, 20 and 10. If we look firstly at the data for 10 degrees, for cucumbers stored at 10 degrees C, we found that 0.1 part per million is a common concentration of ethylene in the marketplace, and this gives a 17-day storage life. If you go to 30 degrees, we found that 1 part per million is a more common ethylene concentration in the marketplace. And here you've got only a 3-day storage life, which is what people expect. You get rapid deterioration. But if you could reduce the ethylene concentration to 0.001, you can get a storage life of 16 days. In other words, you could store at 30 degrees in low ethylene, you get the same benefit as storing at 10 degrees without controlling the controlling ethylene. So for a 16-day storage life, you don't need refrigeration. Now the graph at the bottom, the table at the bottom, shows the respiration rate at 30 and 20 for the various ethylene concentrations. And reducing the ethylene also reduces the respiration. You can see at 0.001, it's only 1/3 of what it is at 1 part per million. Reducing the respiration gives you better retention of taste and texture. Well, we then looked at golden squash, and similar to cucumber, the recommended storage temperature is 10 degrees because you get chilling injury at lower temperatures, and higher temperatures, browning or rotting determines the storage life. I just want to look at the data we got for storage at 30 degrees in the 4 ethylene concentrations. In the normal marketing situation, where you get 1 part per million ethylene, you've only got a 4-day storage life. However, if you can reduce this to 0.001, you get 13 days storage life. So the trader or grower has got an extra 9 days in marketing options, which allows them sufficient flexibility. We then looked at bitter melon. Bitter melon is sort of widely grown in developing tropical and subtropical regions in many Asian countries. But it's growing in popularity in many Western countries. It's almost become a functional food. It's considered to have health properties. In particular, it assists in the control of diabetes, which is a rapidly growing disease of affluence. Bitter melon develops chilling injury below 10 degrees, but it has rapid yellowing above 15, so there's a very narrow window of temperature where you can store it. We decided to look at, well, what's the storage life at 30 degrees and 20 degrees? And you can see that there's a big effect of ethylene, particularly when you get to 1 part per million. As you reduce the ethylene, there isn't that much difference between storing at 30 and 20. But if you go from 1 part per million down to 0.1 parts per million, you get an extra 2 days in market life. And I believe this greatly assists in local marketing. You might say, well, 2 days is not very much, which is why I put this photograph in the bottom right-hand corner. After 3 days at 30 degrees, it's clear which bitter melon you would buy. It's the one stored in 0.001 part per million. No one would buy the 1 part per million. So the deterioration is so rapid. Having the 2 extra days does give a trader a great marketing advantage. Well, the last example I want to talk about is the degreening of lime fruit. Limes have a high price for green fruit and they're not worth very much as yellow fruit. It's recommended that you store limes at 5 degrees, which is above the chilling injury threshold, to maintain green colour for the longest. We stored limes in 5, 20 and 30 degrees in our 4 ethylene concentrations. And you can see that even you put it at 20 degrees, yes, it's less than 5 degrees, but when we stored it at 30 degrees, we were quite surprised. The green life is actually greater than it is at 5 degrees. Now there's a rapid fall off at 1 part per million, but if you've got 30 degrees and can maintain the ethylene below 0.1 part per million, which is not too demanding, you get a great retention in green life, which is much better than you get at 5 degrees, certainly at 20 degrees. Now this has to be more cost effective in tropical regions to be able to hold it at 30 than at 5. And I also wonder whether it's cost effective in warmer temperate regions, say in Spain or the Mediterranean region during spring and summer, where it's cheaper to provide heat up to 30 degrees than to cool to 5 degrees. Well, I just want to finish by going through a number of projects that we're currently involved with. First is with the University of Tasmania. The Australian government is keen to support development of the Australian food industry to make the local supply chain sort of more efficient and to promote exports. And through the Australian Research Council, which is the ARC, they set up a series of training centres. And Tasmania has got one for innovative horticulture products. Now, the requirement for these training centres is that you get a group of universities that get together, but they've got to have industry partners. And the industry partners for this CRC for innovative horticultural products is Woolworths, which is the major supermarket in Australia. You've got these series of fresh fruit and vegetable farms. These are large farms which control marketing from the farm into the retailer. They're very well financially set up, they're into technology, and they're receptive to changing the way they do things. So the training centre has very good farm to market linkages. Now Bioconservacion and DuPont have agreed to be associated with the project, and the agreement is that we would work on berry fruits. It was initially with strawberries, but now they want to also work on raspberries and blackberries. It was on lettuce packs, and they wanted to also work on bananas, although I can't see how they can do it from Tasmania, which is the climate is a bit like England. Now what we wanted to do in the study was determine where the ethylene accumulates in the market chain, quantify the quality improvement by removing or reducing the ethylene, and demonstrate the benefit to industry partners. Now the establishment of the project has been delayed mainly because lawyers on different sides have sort of been arguing about words which will never mean anything in the end. But my counterpart at the University of Tasmania, of course, has been out to their industry partners talking about what we want to do. And I get the distinct feeling that the industry people have already accepted that this technology will work. And they're thinking beyond what we are thinking of as putting sachets of that into packs or boxes. They're wanting to know, can they put it into containers, can they put it into storage rooms? And I've already spoken with Brent that he'd better get his butt down there and start selling them some product, because they're really receptive to removal of ethylene. Second project is in Laos. The Australian foreign aid budget, a large part of it is funneled through the Australian Centre for International Agricultural Research, or ASIAR. And they fund projects which build capability for improvement in food and agriculture in developing countries. And they funded one in Laos to reduce post-harvest losses. Now the project manager is a former PhD student of mine, and she approached me, knowing that I'm working on ethylene, to try and include a project on ethylene removal into their portfolio. And we've agreed on a sub-project where we want to see if we can extend the storage life of vegetables marketed at ambient temperature so that they can go to more distant local markets, or to export to neighbouring countries such as Cambodia, Vietnam or Thailand. And we're just going to say we'll buy on sachets, give them a useful extension. The main crop we're interested in is cucumber. We've started on tomato. They seem to think, well, they've got tomatoes there and we wanted to encourage them to get going. This is data from the first trial that we ran. The way they market them at the moment is in a 10 kilogram styrofoam box. As you can see, they don't do any sorting, so there's ripe to green fruit in there. We scored this fruit on a colour scale where 1 is green and 6 is fully ripe, and we get a colour score of 3.5. Now our treatment was to add 2 5-gram bind sachets, which is a bit of a tall order because it's 1 gram per kilogram. We then held it 3 days at ambient temperature, which in this trial was over 35 degrees, and this is what the fruit looked like after 3 days. There was a delay in ripening. You can see from the colour score that the one with the bind sachets hardly changed from what it was when we started, whereas the untreated 6 is fully ripe, 4.8 is fairly ripe. Now, it's a bit hard to see, but this group of bind sachet, that's the same colour. That's the same colour group as this one here. Now, we've gone back to them and said, look, it's a bit silly. Do you want to extend the marketing life of tomatoes? How about taking out the ripe ones out of the box? So in the second trial, we've only had either green tomatoes or ones like this where they've just started to ripen. We're mostly the way through the second trial, and again we're getting a good reduction, but I'm suspecting that we don't have enough bind product in there, and I might get them to put 4 sachets into the later trials. we're hampered because we don't have any capacity to measure the ethylene in Laos. Right, the next project is in Samoan-grown breadfruit, and I mentioned this at the 2016 meeting in Barcelona. Breadfruit is a tropical climacteric fruit. It's consumed unripe as a starchy vegetable similar to potato. Now, we finally managed to get a 3-year funded project from ASIO. It started in July 2017, so it's fairly new. Our aim is to export breadfruit by sea to New Zealand. It's uneconomical to send them by air. So what we need is a market life of 28 days to allow for harvesting, accumulation while waiting for the ship to come, the voyage, and then some market life. Now, we must prevent ripening. Consumers don't want it when it's ripe. And you could get this by reducing the temperature, but at low temperature, of course, you get chilling injury. So we explored a range of temperatures, and where we are at the moment is at 17 degrees C, we can get a storage life of 20 days. At the end of 20 days, the fruit have ripened. If we go down to 15 degrees, the fruit doesn't ripen, but in 17 days it develops chilling injury. We're now asking, well, will low ethylene give us the extra days either to inhibit the ripening at 17 degrees, or will it inhibit chilling injury enough at 15 degrees to give us the 28 days? And we're in the process of designing the trials to test this. All right, I want to now talk about some new gases. I said ethylene was unique and it was sort of the gaseous plant growth regulator. We now know there's 2 other gases that are plant growth regulators, nitric oxide and hydrogen sulfide. Now, nitric oxide was considered a toxic industrial pollutant. However, in the late 1980s, it was discovered that it was synthesised by mammals, and it regulates many metabolic functions, including the dilation of blood vessels. And nitric oxide in medicine has now found use in treating cardiovascular disease and treating asthma. And the people who made the discovery were actually given the Nobel Prize for physiology and medicine. The most notable use of nitric oxide is in Viagra. What Viagra does, it stimulates the body to produce more nitric oxide. And the nitric oxide dilates the blood vessels in the penis, and hence you have an erection and you're in business. Now, in the 1990s, on a visit to Israel, I met up with this professor of biology, Yaakov Leshem. His colleagues told me, he's a bit of an ivory tower dreamer. He seems to think that nitric oxide could have benefits in post-harvest fruits and vegetables. Now, while they thought he was a bit stupid, I could see the value in it, and we then teamed up and we did experiments in Israel and in Australia, and we showed that adding nitric oxide has considerable post-harvest benefits. Now, while we worked on the reactions, we think the important interaction is that nitric oxide is actually produced by young fruits and vegetables, so it's a bit of a juvenile agent, whereas ethylene is produced when aging, so that if you give the produce nitric oxide, it seems to think it's too young to get old, so it stops senescing. Now, normally the media in Australia is not particularly interested in post-harvest horticulture news, but because of the association of Viagra, they all wanted to write about it. And this is the sort of headlines that used to get Viagra, the secret to hard fruit. And one of the questions just about every reporter used to ask was, well, will Viagra produce straight bananas? The next gas is hydrogen sulfide, rotten egg gas. Again, previously considered a toxic industrial pollutant. It wasn't found till after 2000. Again, it was found synthesised in mammals, and it regulates many metabolic functions, and it seems to interact with nitric oxide. Now, the work on post-harvest effects really didn't start till after 2012, so it's very recent. Our work, which is in the last couple of years, we've shown that H2S actually inhibits ethylene production and inhibits ethylene action. My question then is are these gases a threat to ethylene absorption as a commercial technology? NO and H2S we know are effective in extending post-harvest life. However, there's a range of logistical and safety problems in fumigating the produce, because you've got to fumigate the produce for a short period before storage. It's then a question of who's going to put up the millions of dollars to gain regulatory approval. You can't patent it, so no one's going to have an assured revenue stream. Therefore, I can't see anyone being prepared to put up the money. But the threat doesn't come from using the gases, it comes from their amino acid precursors. Our own work has found that arginine, which is a precursor of nitric oxide, inhibits the browning of fresh cut produce. Now, we've only done a couple of them. Cysteine, which is a precursor of hydrogen sulfide, we found to inhibit the yellowing of leafy vegetables. Now, both arginine and cysteine have GRAS status. In other words, they're generally regarded as safe. Now, compounds in this category, it's very easy to get approval to use in foods, and both arginine and cysteine have already been allowed as an additive in some foods. So there is the potential for arginine and cysteine to be a competitor to potassium permanganate. And will it come down to cost or ease of use as to what industry prefers? Right, in trying to summarise, say, well, why should we use ethylene absorbents? Well, firstly, to reduce costs, and there the refrigeration energy saving wants to be greater than the cost of the new technology. Secondly, I could see shipping replacing air transport in quite a number of cases. Firstly, you can increase the volume, and of course it's a much lower cost. There's the marketing advantage, where in developing regions, as I've said, you can send to more distant markets and you can have better control over market timing. There's also a marketing advantage in reducing greenhouse gas emissions. You can promote this as having green credentials. I could see, for example, that say Ecuador was sending bananas without refrigeration. They could say these bananas were brought to you in France with 80% less CO2 emissions than bananas from everywhere else in the Caribbean. Now, what are the barriers to change? I think the greatest barrier is the risk-averse nature of the industry. When I talk to managers in these vertically integrated companies, they sort of believe what you're saying, but they take a deep breath and look out the window. It's too risky for them to introduce a technology where you reduce the use of refrigeration, and they don't want to risk their jobs. Maybe we've got to go through a period of incremental change where they bring it in, see it does any harm, then gradually increase the temperature. The other barrier to change is the inability to quickly analyse low ethylene concentrations. This was an issue raised at the 2016 meeting and it's still an issue today. With the measurement of ethylene, we need a method that's sensitive, fast, cheap, and portable. What we want to do is make industry players constantly aware of the ethylene concentration in their packages or in their storage containers or transport containers. We want it to be similar to temperature measurement, where there's a thermometer in container, anyone can read it at any time. You can have thermoprobes, temperature loggers which read out on the computer so you're aware of the temperature at all times. We want something like that for ethylene. But we need to analyse ethylene down at least to 0.1 parts per million in air, ideally down to 0.001 parts per million. Instrumental methods at the moment can do this. They're quick, but they're expensive, and most of them are not portable. The rapid methods are available, such as alcohol breath type tubes, but they're not specific for ethylene. They tend to pick up a whole lot of oxidisable compounds. What we need is a method that reacts only with ethylene, and it generates a colour or an electronic signal which we can then measure. I've gone to different meetings and people talk about some new technology they're developing, and I raise it with them. Can you measure ethylene? And they give you positive signs, but when they go back and think about it, they come back and they don't think so. Best hope, I think, is an ELISA type assay. ELISA means enzyme-linked immunosorbent assay. And what it is, you have a tube or a plate with some extract on, you expose it to gas or liquid, it reacts often with a colour or with some electronic signal. What we want is some enzyme extract from produce or something which simulates an enzyme extract, attach it into a tube or a plate and let ethylene react and measure the signal. Secondly, I think we want a quick visual test to know when the potassium permanganate sorbent is about to expire. At the last meeting I showed data that says, well, just looking at the outside of whole beads is not a good indicator of whether it's still absorbing ethylene. And why you need it's not necessarily for your own purposes, but it gives confidence to people that are using your product that when you say they should change it, it's because it's running out, not because you're wanting to sell them more product. So they really want a test where they can crush a bead and get a quick answer as to whether it should be changed because it's not absorbing enough, or it can go on for a bit longer. Okay, so thank you, and let's give the big hit to ethylene.